Chapter 5, we'll be doing differentiation and integration of new functions. We'll be starting with the natural logarithmic function, and in part 1, just taking the derivative of it. So let's talk about that natural log function. It's the basic parent function is the natural log of x, and it's written ln of x. What it is a log with base e. So e is the number, the Euler's number e, 2.718281828 blah blah blah, etc. It's not a pattern, it's an irrational number that continues on forever. And the mathematician Euler was the one who discovered this number and started using it, so he gets to call it the letter E for Euler. Euler is a German word, E-U-L-E-R, so E stands for Euler. Anyway, it's a log base E. Other logs that we've used are log base 10 is the common log, and so log base E is called the natural log, and it's the letters ln and then of x. The domain is only positive numbers. It's always, you can only put positive numbers into a natural log, and its range is all reals from negative infinity up to positive infinity. So let's think about the function natural log of negative x. How is that graph going to be different than the function natural log of x? If you put a negative on the inside of a function, what does that do to it? Let's look at our graphing calculator. If we're going to graph the natural log function, go to your y equals. Here's the ln button, and we'll type in a negative x. And do a zoom 6 to get a standard window. And it just reflects it over the y-axis. So that follows what we've talked about before. If you put a negative inside of a function, it will reflect over the y-axis with certain types of functions. What about the function natural log of x minus 2? Well, inside of a function, if you subtract 2, it should move it to the right 2. So let's check that out. Go back to this function here, natural log of x minus 2, and graph it. Compared to our original function, you can see it moves it to the right 2. The graphing calculator doesn't draw this line here. That goes, it actually goes down. It continues to go down here. I guess I can't draw on this, but it continues to go down here. So it's got a vertical asymptote here. So I could draw it over here, vertical asymptote at 2. And it goes like that. So this point 1, 0 is now at the point 3, 0. Every point is moved to the right 2. This vertical asymptote at 0 for our original parent function is now moved to the right 2, so it's at x equals 0. What will the graph of natural log of x plus 5 look like? Well, if you add 5 to a function, it should move everything up 5. Let's check that out. Natural log of x, close the natural log function and then add 5 to the end of it. And it does move everything up 5. So this point at 1, 0 is now at the point 1, 5. So this graph will look like that. And then the graph of negative natural log of x. If you multiply this function times a negative, it should reflect over the x-axis. And it does. So what that demonstrates is that this function behaves the way that all of our other functions behave. It's got an asymptote. That asymptote will move right or left depending on if you add or subtract a number inside. It moves vertically if you add a number outside. If you multiply it by a negative, it reflects over the x-axis. And if you put a negative inside, if you multiply the number inside by a negative, it will reflect it over the y-axis. What's happening at the natural log of e? Let's see. E is approximately the number 2.71828. So if we go back to our original natural log function, parent function, and we trace until we get to about 2.71828. it's about 1. We can type in the letter E, which is right above the natural log button. So once you've hit trace, if you type in a number that you want, we want e to the first, because that's what e is. E to the first is e. You can see that y equals 1. The natural log of e equals 1. That will be important for us. So the same rules apply for common logs. The same rules that we had for common logs apply to natural logs. The natural log of a product, a times b, would be the natural log of a plus the natural log of b. The natural log of a to a power will be n times the natural log of a. So that power is multiplied times the function natural log of a. Natural log of a over b is the same as natural log of a minus natural log of b. And these two you need to memorize. The natural log of 1 is 0, and the natural log of e is 1. So let's use those log properties. Let's expand the natural log of x times x minus 5 to the 5th power. First, we're going to deal with this product here. Natural log of x plus natural log of x minus 7 to the 5th. Then we're going to deal with that power. The property says we can put the power out in front, but just in front of the quantity that is raised to the 5th power with the natural log, so that 5 is just going to go here. It does not go to here. We cannot do the 5th power first out in front of here because that 5th power is not on this x. So that's expanding using log properties. That's as much as we can expand it. You cannot expand a subtraction or an addition quantity inside of a natural log. So that's as expanded as it gets. And we can do the opposite. We can condense using log properties. So going back to these log properties, if I have this, I'm going to condense it by going to that. Or if I have this, I can condense it by writing it like that. So expanding is using the property from left to right. Condensing is using it from right to left. So first thing we notice is this 3 is times everything. So that means that 3 is basically a power out here. So we can put the power out in front first. Take the power out in front and put it, oop, I don't need that parenthesis there. We could put it on this whole thing here. Then we notice that we've got a subtraction sign and multiplication sign. I'm sorry, a subtraction sign and an addition sign, and we've got this 5 here. Let's deal with that 5 first. So that 5 is going to go up here as a power on the natural log of x, so it's natural log of x to the 5th. And then we still have this, and we still have this. So taking care of this, the condensing property would mean we have natural log of 3x plus 7 divided by x plus 2, and then plus natural log of x to the 5th means we're going to multiply by x to the 5th. Finally, I would probably write it as natural log of x to the 5th times 3x plus 7 all over x plus 2. And you don't need those parentheses in the denominator if you don't want them. So you could just write it like that. And that's condensed. The reason we have to review these properties is we will be using them to help us find derivatives. Okay, let's define e. The natural log of e is the integral from 1 to e of the function 1 over t dt. And that equals 1. So this is the formal definition of the natural log. And until you understood what integrals were, you couldn't even talk about what the definition of natural log of e was. So then the natural log of x, this function, natural log of x, is the integral from 1 to x of 1 over t dt. So then what is the derivative of natural log of x? Remember, if we take the derivative of this, then we're taking the derivative of this. Derivatives and integrals cancel each other out. We've got a constant down here and a variable up here. So the second fundamental theorem of calculus says that if we're doing the derivative of an integral with a constant here and a x here, we can just replace that x in for the letter t. So that would equal 1 over x. Now, until we had the second fundamental theorem of calculus, we couldn't evaluate this integral from 1 to x of 1 over t dt. Let me remind you why. If we want to integrate that, our first inclination should be to rewrite that as t to the negative 1. Now that looks like we can use the first fundamental theorem of calculus, which says we can add 1 to the exponent and divide by the new exponent. If I add 1 to that exponent, I'll get 0. And I divide by that new exponent, I'm dividing by 0, which you cannot do. So this, up until now, has been a dead end. But now that we know that the natural log of the integral from 1 to x of 1 over t dt is the natural log of x function, now we know that the derivative of that will just be 1 over x. We'll get more in depth on this in a minute, or in tomorrow, but for now, just know that the natural log of x function equals the integral from 1 over x of 1 over t dt. And that's only when x's are positive there. Okay. Yeah. So the derivative of natural log of x is 1 over x. You've got to memorize that. And if we have a function inside of our natural log, so if it's not just natural log of x, but it could be natural log of 3x plus 7 or 2x squared minus 4x plus 1, any type of function inside of a natural log, it's still going to be 1 over x, but in this case it'll be 1 over u, 1 over that function, and then times the derivative of that function. So it's like a chain rule. You do the derivative of the outside, which would be 1 over the function, and then times the derivative of that function. So some people just like to write u prime over u, because this is the u prime part, and then this is u. And remember, u has to be greater than 0. So let's do this example. If y equals natural log of x to the third, notice this one, our inside function, is the natural log of x, and our outside function is u to the third. So the derivative is 1 over x, that's the new thing we just memorized, and the derivative here is 3u squared. So using our chain rule, we're going to multiply those two pieces together. The derivative of y equals 1 over x times 3, and then instead of u squared, I'm going to put u back in, which is natural log of x. So that's the derivative of the function y equals natural log of x, all of that to the third power. Just to review how to find the slope of a tangent line, this is the slope equation of any tangent line at any point on the function y equals natural log of x to the third. We want the slope of the tangent line at 1, 0. So when x is 1, I want to know what the slope is. Well, here's my equation for slope. 1 over, and I'm going to put x in. Put x in. X is 1. What's the natural log of 1? Remember I said you had to memorize that. It's 0. 0 squared is 0. 3 times 0. So y prime is 0, which means our slope is 0 at the point 1, 0. So what's the equation of the tangent line? Y minus y1, this is our y1, equals m times x minus x1, which simplifies to y equals 0. So we have a horizontal tangent line at y equals 0. There's our homework, page 331, 7 through 17 odd, 21 to 53 odd.